Pandey, and I welcome all of you to the Study Bay Technologies. In our lecture for Signal and System, it's our third lecture actually, and in our today's session, we will discuss a few details about elementary signals. Okay, so these elementary signals are basically the building blocks for the construction of more complicated signals. So these elementary signals include exponential signals, sinusoidal signals, step function, impulse function, and ramp function. Okay, so let us discuss all of them one by one. So first of all, we have exponential signal. You can see here the details of both continuous time and discrete time scenario. For continuous time, it is like xt is equal to b into e to the power at, and in discrete time, it's xn, that's equal to b into r to the power n. Now, at this b is basically amplitude of the exponential signal, and this is measured at a time t equal to 0. Okay, that is the moment when we switched on the switch. Similarly, we have a few cases related to each of them. Related to the continuous time, we have a less than 0. In that case, the exponential signal can be considered as decaying exponential signal, that is decaying in nature. The graph of the concerned exponential signal will be decaying in nature. Okay. Similarly, it is a greater than 0. In that case, the graph will be growing in nature. Okay. Similarly, in case of discrete time, if the value of r is lying between 0 and 1, in that case, the graph will be decaying in nature. And in case r is greater than 1, in that case, it will be growing in nature. Okay. Similarly, if r is less than 0 in case of discrete time signal, the graph will be showing as alternate time. Means sometimes it will be positive, sometimes it will be negative. Okay. So this is all about the exponential setup actually, and this is how it actually looks like. So you can understand very well that this type of graph is basically decaying in nature. Okay, because in our physical environment or in practical setup actually, almost all these setup, all these functions, all these physical entities, they present a loss, and in that case it will be decaying in nature in most of the cases. Let's try to understand it with some basic kind of signal. So this is how the below you can see stepwise graph actually. That is again for the discrete time in nature, and you can see here that still it is decaying over there. Okay. Moving ahead, let's try to understand these kind of decaying exponential signals by getting some explanation from RC circuit, that is resistance and capacitor circuit. Okay, this capacitor here is called as your lossy capacitor, and the resistance here is called as shunt resistance. So what happens actually that the capacitor is first of all charged by connecting a battery across it, and then the battery is removed at the time t equal to 0. And thus the initial value of the voltage which is developed across the capacitor is V0. Okay. Now, just after removing the battery at t equal to 0, when we have started the circuit, that is the operation of capacitor for time greater than or equal to 0 is described as RC dV by dt plus Vt is equal to 0. That is the current which is flowing through the system. Okay. Now, this is actually a differential equation of first order. Right? This Rc dv by dt plus Vt is actually the differential equation of the first order, where Vt is actually the voltage measured across the capacitor at time t. Right? I hope you have got the concept. First of all, we have charged the capacitor to voltage V0. After that, we have removed the battery. Now current is flowing through the resistor or shunt resistor, and then the voltage is decreasing, right, across the capacitor. So what happened? If we try to solve this differential equation of first order, the output will be something like the voltage across the capacitor at time t greater than or equal to 0, it should be V0, that is the initial voltage, into e to the power minus t by Rc. Here this Rc is called as your time constant. Okay? So this is how your graph of this exponential signal will be decaying in nature. Okay? And this is how the entire process takes place. So this involves a few more points, like as per this equation, this voltage across the capacitor decays exponentially with time at the rate which is determined by the time constant Rc. Okay? And larger the value of shunt resistor, that is R, slower will be the rate of decay of the voltage. That is with time, that is less lossy will be the capacitor. Right? So this is how you can understand like how this process is actually going on. Now let me give you some basic idea, or let me give you some real-time scenario that where we can use these kind of signals or exponential setups actually. Right. So the thing is, like, let's say in case of decaying scenario, that is utilization of these signals and systems in medical science or in nuclear reactors as well. So let's take for an example, let's take one scenario over here. Say that there is some kind of interconnected system, that is system 1 and system 2, and some decaying process is going on over there, right? And we have, some, let's say, some 20 ml of system, or some, material or radioactive material, which has around 5,000, that is the 5,000 number of cells, right? And I would like to, initiate the system number 2 if we have 1,000 cells left, right? And the situation is something like, let's say, after every minute, 45% of cells are dying. In medical science, or in case of your nuclear setups as well, you might have heard about the half-life period, right? Half-life period of radioactive substances. Similarly, in case of medical science as well, like if we have some body part which is decaying at a gradual rate, right? So number of cells will be decreasing at some time. So it's saying that like after every 1 minute, 45% of cell get decayed down. Right now we have 5,000 cells, and every minute this is getting down by 45%. And we need to initiate the system number 2, saying that once we have 1,000 cells are left, in that case only we should initiate system number 2, or we should initiate some kind of backup or anything like that. So let's see how it actually looks like. Let me use Excel, and it will be good for this. For initial time, let's say the initial time, that is at t equal to 0, so the initial value was 5,000, something like 5,000 cells. Okay, so let's start by calculating the same points, graphing the point, and then we will determine what mathematical model best describe these points. So the number of remaining cells at any point of time depends upon the amount of time since the experiment began. That is at t equal to 0 and initial value. Here all the points will have the form, that is the time since experiment began and number of remaining cells. And this sounds complicated, but actually it is not. So let's say at the start of the experiment, no time has passed and t is equal to 0 as you can see here, right? At the start of the experiment, there are 5,000 cells. So the first point is 0, 5,000. Fine. Just after 1 minute, let's say the time is now 1 minute, right? So around 45% of 5 million cells die, and this leaves 27,50,000 cells. So the corresponding point is 1, 2750, 000. These are the number of cells, 45% of 5 million. Okay. Now at time 2, that is after 2 minutes, what happens? Again, 45% of 275,000 cells, 45% have been died, and this leaves around 1512,500 number of cells. Okay. Again, just after 1 minute, again after 1 minute, that means when the third minute has been started, at that time what happened? Again, the 45% of this value got died, and it left around 83,1875 cells, right? Now, if this is the case, and this continues actually like this, okay? And if we can try to plot this in the graph so that we can try to understand what is the nature of the curve, and based on that we can define what kind of mathematical function it is going we are going to use. Let's try to plot a graph for this, and we can see here this kind of graph, right? You can see here this graph clearly shows that it is nothing but just your exponential function, right? So in that case, let me use my notepad. In that case, it's something like we have a mathematical model which is exponential in nature, and we can take it as something. Let me. So we can derive a function for this exponential graph as we have just seen over here like this. It is something like let's say this is something as ft, mark it small, ft is equal to, we can put some equation a into let me insert the equation e to the power bt, that is e to the power bt. It's something like this. This will be my corresponding equation like this for the concerned graph. Here ft is number of cells that remained in t minutes after the experiment started. So let me write it for your reference. The ft, this is number of cells remaining in 2 minutes after started. Let me put no spacing here. Okay. Now this A, what is this A here? This A signifies the number of cells at start of the experiment. Okay. Number of cells at the beginning of experiment. How many number of cells were there? It was around 5,000 cells, right? We can make it 5,000 cells. Fine. Similarly, T, what is this T over here? T is number of minutes since experiment begun. Here B is basically called as decay constant at time T. Okay, so yes, we can calculate this value of B as well by putting all the concerned data over here. Okay, and since this is a decaying exponential, as you can see here, the value of B should always be in negative, right? So this is one of the case where you can use this exponential setup, right? So similar kind of cases, and one can consider regarding the half-life period of a radioactive substance as well. Again, just assume a same kind of a use case in a nuclear reactor also. There are let's say there are two different interconnected systems. The system one is actually monitoring the radioactive substance with a half-life period of, let's say, 8 days. That is monitoring the decay signals, right? And the initial amount of the that is substance is 2 grams. A system will get initiated when 0.01 gram of substance remains, right? So this is again a kind of an intelligent system where we need to write some programming logic as well for the same. And by this kind of scenario, this kind of the technique, whatever you have learned today for this signal and system setup, you can apply it over your algorithm, right? So this is how you need to use your knowledge for building up the systems as well. Fine. Now move ahead. Let's move from here. This is what I have just explained to you. Now something about sinusoidal signal. Sinusoidal signals, I'm sure some of you might have idea about that. In terms of continuous time signals, these are called as xt as equals to a cos omega t plus phi. And in case of discrete time, it is xn is equal to a cos omega n plus phi, where this a is actually the amplitude, omega is frequency. In case of continuous time, it is called as using the unit as radians per second, and in case of discrete time, it is using radians per cycle. And phi over here is a phase angle which is measured in terms of your radians. Okay, so let's say this is how your continuous time sinusoidal signal are generated. And similarly, if we talk about discrete time, this is how it actually looks like. So now, let's take one more example about the generation of sinusoidal signal. For this, we can explain the LC circuit, that is inductor and capacitor circuit. Here, the inductor and capacitor are connected in parallel. So first of all, the voltage developed across the capacitor at time t equal to 0 is called as V0. And the operation of the circuit For time greater than or equal to 0, we can see here it's like LC d2v by dt square plus vt is equal to 0, and this type of equation is actually called as differential equation of second order, where the Vt is actually the voltage measured across the capacitor at time t. Here C is the capacitance and L is your inductance. And if we try to solve this kind of equation, the equation will result in something like Vt is equal to V0 cos omega 0 t. Okay? Here omega 0 is your natural angular frequency, or it's also called it as your time constant. Now, in terms of this discrete time signal as well, the scenario is same as you can see here, something like this. In terms of discrete time signals, it actually comes out. Okay, so specifically for the discrete time sinusoidal signals, if they require to be periodic, the angular frequency must be a relational multiple of 2 pi, right? So the thing is, like in our last video, we have already explained you like why do we use these sinusoidal signals. The point is something like that the sinusoids play a very much important role in audio processing, because if you shift one of them left or right by any number of samples, you get another one. And this makes it easy to calculate the effect of all sorts of operations in sinusoids. Here our ears use this same special property to help us pass the incoming sound, which is why sinusoids and combination of sinusoids can be used to achieve many musical effects. Okay. Now there is something called as exponentially damped sinusoidal. You have already seen about decaying exponential signals, right? So what is the case? Like if we combine both exponential signal or decaying exponential signal along with the sinusoidal signal. So in order to understand this, we have a parallel circuit of RLC, that is resistance, inductance, and capacitance. Okay. So the multiplication of sinusoidal signal by a real valued decaying exponential signal results in a new kind of signal which is referred to as exponentially damped sinusoidal signal. Okay? So in order to understand this, we need to understand a few points like current through the resistor. It can be given by V by R, or that is Vt by R. Current through the inductor, it will be given as 1 upon L integral from limit minus infinity to t, d tau, d tau. Tau is the time limit. Similarly, current through the capacitor is C into dVt by dt. Alright? You know very well that combination or addition of all these properties, all these current actually returns 0. Right, that is Vt by R plus 1 upon L integral minus infinity to t V tau d tau plus C Vd dVt by dt is equal to 0, and this kind of equation is called as integral differential equation. Okay, this integral differential equation, if you try to solve this, you'll get an output of something like V tau is equal to V0 e to the power minus t upon RC cos omega naught t, and omega naught, that is the natural frequency, is under root 1 upon LC minus 1 upon 4 C square R square. And this is how at the bottom you can see this exponentially damped sinusoidal signal looks like. Okay. So in a similar case for discrete time as well, we have xn b r to the power n and sine omega n plus phi, which is almost equivalent to this its own um, continuous time counterpart. Okay. Similarly, we have something called as step function. So under this continuous time, we have ut which is equal to 1 if t is greater than or equal to 0, and it is 0 in case t is less than 0. And a similar case, if n is greater than or equal to 0, it is 1, and it is 0 in case n is less than 0. This ut is, or in fact, the step function is actually represented by u, and the step function is particularly simple signal to apply. Battery or DC source is applied at t equal to 0 whenever we are closing the switch. And as a test signal, it is useful because the output of a system due to step input reveals a great deal about how quickly the system responds to an abrupt change in the input signal. So this is how it actually looks like in terms of your continuous time and its discrete time counterpart. Okay. Then we have impulse function. Impulse function is again it is continuous time and discrete time. And under the continuous time, it is 0 for all t not equal to 0, and integrals from minus infinity to infinity. The integral of impulse function is equal to 1. This simply means that the total area under the unit impulse function is unity. And under this discrete time, this sigma n, sorry, uh, delta n is equal to 1 for n equal to 0, and this impulse for n equal to 0 for n not equal to 0. Okay? Now, this is how it actually looks like. In the first diagram, you can see here that it doesn't matter how much you stretch it or how much you expand it, the total area occupied by the concerned impulse function will be unity. Okay, so impulse function is basically zero everywhere except at the origin, and this impulse function is also called as Dirac delta function. And whenever we speak about impulse function, in effect, we are saying its strength in unity. And remember that this unit impulse function is an even function of time t. Okay. Similarly, we have one more function that is called as ramp function. So ramp function is again specified by r of t is equal to t if t is greater than or equal to 0, and it will be 0 in case t is less than 0. And in the same case, we have this for the discrete time setup as well. This is equal to n in case if n is greater than or equal to 0, or it is 0 if n is less than 0. You can see this under the graph what I have shown you below for both continuous time and discrete time. Right. So the thing is like about its application, the input variables over there. There is angular displacement of a shaft at constant speed of rotation of shaft provides a representation of the ramp function. Okay. And as a test signal, the ramp function enables us to evaluate how a continuous time system could respond to a signal that increases linearly with time. Okay? So these are the uses, these are the basic, idea about different types of signals. Okay, so now let's try to understand a few interrelations. Let's say we have a step function. You can see here the graph. In case you differentiate the given function, it will give you impulse function. It is something like this. And in case you integrate the step function, it will give you the ramp function, something like this. Right. So we'll make use of these techniques in our later chapters as well, and where we will be, generating different kind of signals. As an electronics engineer, we might have to create a differentiator, or we might have to create an integrator also circuit in terms of a circuit, and we have to use or utilize these kind of signals as per our requirement. Right? So that's all for today's class. In our next class, we will study about interconnection of systems. These are the details about basic elementary signals. If you have any question, any doubt, please feel free to ask me on this, on your comment box, and kindly like, share, and subscribe this video so that it could reach larger number of audience. Have a nice time ahead, guys, and take a very good care of yourself. Bye bye.